Good morning, everybody. I think, so some of the context for this talk you're going to hear today is that in 2007, I started at DARPA as a program manager, and I started a project called Synapse, which was a neuromorphic computing project. You may have read about a large chip that IBM built and so forth. And that was the first project I started at DARPA. And, I learned a lot doing that project, honestly. And then the second project I started at DARPA was called Physical Intelligence. And I called the goal of that project was to figure out what the heck intelligence is and with some sort of physical foundation. That was a much harder project, frankly. And I had a hard time keeping it alive because nobody could understand what I was trying to do, including me, perhaps. Interestingly, about 3 years ago, there was a workshop held in this very room called the Neuro-Inspired Computational Elements Workshop. I know Bruno was there. And there was a panel up on stage talking about neurally inspired computing, and I was out in the audience where you are, and I was going like, hey, if you can't figure out how to make these things organize themselves, you're going nowhere because they're too damn hard to program. And then there was a lot of dislike of that comment, but that's really sort of what I learned while doing the Synapse project at DARPA, which is that you could build a large-scale neuromorphic computer, no problem, and it could do a lot of cool stuff in principle. But it was hard to make it do something in practice because we didn't have the foundations to understand how to make it organize itself, frankly. So that drove me in this direction that I call thermodynamic computing. So here's the outline for the talk. I'm going to give some motivational ideas. I'm going to talk a little bit about thermodynamics. I'm going to talk about a vision for thermodynamic computing, which is, I think, going to be the next stage of computation. And then I'm going to present a neural network model that I call the thermodynamic neural network model, which I've just recently completed, where I try to incorporate pretty much all of the ideas that I'll have brought up in the earlier parts of the talk. And this model is now available online. You can look it up on GitHub. There's a manuscript. There's all the code if it turns out that you're interested in it. And then a few conclusions. So motivation. So just a few observations. Computing absorbs about 5% of U.S. electrical power production today. And if you look at the projections of where we're going, in a few decades, we're going to use all the power in the United States to run our computers. So next generation semiconductor fabs are projected to cost $20 billion. Moore's law is clearly on its last legs. And electron devices are comparable in size to biological molecules. And for that reason, thermodynamic fluctuations are a challenge. And just as a comment, I'll say paradoxically, while we work really, really hard to get all the fluctuations out of the hardware, we create them in software to sample probability distributions and to train models. So there's a kind of interesting sort of paradox I see there. However, we're still at least 1,000 times above the Landauer limit for thermodynamic efficiency in computing. Our computing systems today possess far, far more potential to do things than we will ever be able to program. There's simply too many things, too many degrees of freedom. We can only do a very, very small thing, very, very small number of things that we can do on these gigantic machines that we build now. And we're still many orders of magnitude less capable and less energy efficient than brains. So my conclusion is, we're in the late stages of a mature technology, but we're still a long way from the fundamental limits. We're missing something, is my conclusion. So a few more thoughts. I think that the primary problem in computing today is also what I said about neuromorphic computers, is that the computers cannot organize themselves. We have trillions of degrees of freedom, mostly doing the same stuff over and over again. Machines are ill-suited to evolving complex real-world problems. So machines can transform energy from one type to another, but they can't evolve because they are literally frozen. They are too cold. And my final comment here is that machine learning systems universally employ thermodynamic concepts. However, they are still mostly ad hoc solutions that lack sort of an overarching paradigm. So here's sort of high level my hypothesis about why thermodynamics in computing. Why thermodynamics? Thermodynamics is universal. There are no fields of endeavor or of human understanding where thermodynamics is not the primary concern. Thermodynamics is temporal. The second law of thermodynamics is the only reason we know that anything should ever change. Okay? Thermodynamics is efficient. What I mean by that is that the thermodynamic systems that evolve in the world, whether they are natural systems or technological systems, always strive for greater thermodynamic efficiency. And lastly, I'll say is that thermodynamics is not mechanistic. It can't be described as a machine. Can't describe the second law of thermodynamics mechanistically. I think that's important. So my hypothesis here is that thermodynamics drives the evolution of everything, and that thermodynamic evolution is the missing unifying concept in computation and in probably many other domains as well. Also, I think electronic systems today are extraordinarily well suited for thermodynamic evolution. I'll say a little bit more about that later. And so I believe that thermodynamics should be the principal concept in future computing systems. So now a little sort of framing of sort of where we've been and sort of maybe where we would like to go. So I divide the world up here of technology into 4 buckets. I've got things that are programmed versus things that learn on the horizontal axis. And on the vertical axis, I've got things that are dynamic or online or in the real world versus things that are static or offline or in a virtual world. Now, as a young man, pretty much everything was down here in the lower left. Everything was offline, everything was programmed. I had a computer that sat on my desktop, and I used it to do spreadsheets and things like that. Then in the last few decades, we've made enormous advances, particularly in communication technologies as well as scaling our computers, and so 2 things happened. We were able to take our computers into the real world. These are the phones that we've got with us every day, and they are in the real world, but they're almost still entirely programmed devices. They can do a little bit of adaptation, but only very modestly. And then down in the lower right, we have these ginormous data centers now. And these things, of course, are connected together. There's a big network that hooks them all together. And this lower right piece is largely the domain of machine learning today. But it's mostly offline, and it's mostly on static data sets. Now, the domain that we would like to attack, and certainly the domain that you hear about in the popular technology press, is here. It's in the upper right. In the upper right, we have dynamic online systems in the real world. They pretty much have to learn, because the real world is too complicated to program it. So this is where you've got the self-driving cars and the smart cities and all the many things that we would like to do now. That, frankly, we don't know how to do very well. So what's the problem? Why don't we know how to do it? So here's the same chart, and what I'm doing is I'm putting in what I see are critical ideas in each of these various boxes. So on the lower left, we've got arithmetic and algebra and the stuff of spreadsheets and word processors and so forth. In the upper left, this is the domain of classical physics. Okay, this is Newton's laws, for example, Lagrangian Hamiltonian physics, calculus, differential equations. I call that dynamic modeling. In the lower right, I have titled what I call statistical learning and inference. This is where we have ideas from probability and statistics and equilibrium thermodynamics, and this is mostly where machine learning is today. The question is, what goes in the upper right? And so here's what I'm guessing goes in the upper right. I call it dynamic learning and inference. It should be ideas from non-equilibrium thermodynamics that include fluctuation, dissipation, adaptation, and equilibration in a unified way, and would result in what I call multi-scale quantum thermodynamic evolution. This is the stuff that we don't know how to do. So a little bit about thermodynamics now. So, when I was taught thermodynamics, and I was taught it twice, thought it was incredibly hard. It was all about equilibrium systems, and the key idea that gets drilled into you is that if you take an isolated system, and for some reason it's out of equilibrium to start, I'm sort of trying to represent that by this sort of blue box in the middle. It has some structure to it. You're told that if it's out of equilibrium to start, that over time the system will become more disordered, and so this thing may disperse in some way, and that the entropy of the system will be maximized. And that's pretty much equilibrium thermodynamics. That's what I learned. Thought that was incredibly hard. So that's, an interesting thing, but what we also know to be the case, of course, is that there are no isolated systems that we care about in the real world. Zero. They're all open systems. And in an open system, energy and matter constantly flow into and out of the system, through the system. And in the real world, what happens is exactly the opposite. Constantly, as these materials and energy flow into the system, new structures emerge. Every day, all around us, this happens. Everything you see essentially is doing this. Now, it doesn't violate the second law of thermodynamics because more entropy is being created in the environment in the course of creating this local organization. But it's not what we really understand very well. This is the non-equilibrium thermodynamic pieces that I think we sort of lack understanding of. So my hypothesis here is that one way to think about this is the way I think about it, is that organizations evolve by relieving thermodynamic potentials and creating thermodynamic entropy in the greater environment. Okay? There's potential in the environment. That potential drives the organization of structure, which essentially dissipates the potential. So a few examples of what I mean here. It's just some pictures of stuff that you see all the time. So in the case of the funnel cloud and the lightning bolt, so there's a potential difference between the atmosphere and the Earth, and these structures spontaneously emerge in order to relieve those potentials. These funnel clouds and lightning bolts are spontaneously formed structures driven by the thermodynamics of the environment. Another simple example is when you boil water. Okay, when you boil water, what happens is that bubbles appear at the lower hot interface. And the reason those bubbles are organizations that didn't previously exist. And what they do is they facilitate the transfer of heat from the heated surface to the atmospheric surface. Okay, so an organization spontaneously emerges that wasn't there in order to relieve a thermodynamic potential, is the idea. Same thing for rivers, right? There's a gravitational potential between where the water may be located, because it rains on the top of a mountain, for example, and say the sea. And so what happens is a structure emerges that facilitates the transport of this water from the high elevation to the low elevation. We call those things rivers. So, but it's not just these sort of non-living systems where we recognize that this is happening. It's also the case that if you look at these deep hydrothermal vents, there's an enormous living ecosystem down there, a bunch of living things. And at the very bottom of this ecosystem is a kind of bacteria that's able to eat, essentially, the chemistry that's coming out of the earth. Okay? So my point here is that what's going on in the non-living world goes on in the living world as well. The living world itself derives from things that are not alive. If you looked at the ecosystem as a whole, it is built on things that are not alive. Okay? So my assertion here is that this thermodynamic evolution idea, although I think it's relatively easy to spot here, is maybe not so easy to see in the context of a living system because they're so much more complex. I'll come back to that problem in a minute. So here's an example, from my childhood, which sort of, it's one that maybe many of you have done. So you would take iron filings and you put them on a cardboard or a piece of paper and you bring a magnet up from underneath it, right? And as you do that, this organization spontaneously emerges, right? Which we use in many contexts to say this is what the magnetic fields look like. That's all true. But what my point here is that when you bring that magnet up to the surface, in contact with those metal filings, you can feel the potential. You can feel the work that's being done and the entropy that's being generated in your muscles as you bring that magnet up, okay? If I take that magnet away, then some remnant of that previous organization still remains, so that if I bring up the magnet again in a somewhat different orientation, the previous organization will influence the new organization. So my point here is that this is a way that memory can develop, right? An organization can emerge from one set of potentials which then affect its function or its organization under a different set of potentials. Has memory. Now, recently, Chris Yarzensky, I mean, it's been 20 years now, did this amazing thing where he got rid of the inequality in the second law of thermodynamics, which says, the work is always greater than the change in free energy in a system. And what he said was, well, if you took a system and you drove it sort of from point A to point B with the potential, and you averaged all of the things that it did in this exponential way, that it would equal a similar exponentiation of the change in the free energy. So this is kind of a remarkable result. This is for a non-equilibrium system, and it's an equality, not an inequality, for the second law of thermodynamics. So there have been a lot of variants on this idea, in the last 20 years. I shouldn't say a lot. I should say there's a small community of people who do these things, and they're mostly not well recognized in the larger community. One of the most noteworthy ones was by Gavin Crooks, and his generalization of this idea says that if you drive a non-equilibrium system from one point to another point, and you do that many, many times, and you average the exponential, and then you do the same thing sort of in the reverse, and you took the ratio of those two, what you would find is that ratio is equal to the average heat that's created in the system, okay? So it's a little more detailed than Yarzensky's inequality. That's all it is, but it's the same idea. Yarzensky's equality, I should say. Also, what is recognized by this is that systems driven by external fields tend to organize into states that create high work absorption and dissipation. Those states, those transitions would be favored as compared to their reverse, and therefore they would be favored as compared to a bunch of others who don't create as much heat. Another consequence of these ideas is that, and this is work by Suzanne Still and her collaborators, is that the loss that a system incurs when a potential is driven through it is equal to the amount of non-predictive information it contains. Okay, a system that can perfectly predict what its potentials are going to be, in principle, would have zero loss. Right? So what this means is that systems that are good at predicting their future don't need a lot of energy to do what they do. That's really all that it means, okay? So now let me give you my sort of intuitive interpretation of these non-equilibrium fluctuation theorems. In the high dissipation condition, this is the state of, quote, the novice. When you're a novice, there's a lot of loss going on. There are a lot of fluctuations going on. You have to try a zillion different things, right? It's really difficult. It takes a lot of effort. On the other hand, when you're the expert, you've basically come to understand what it is your environment is doing and how it is you should react to it. So you can seemingly without effort do the things that need to be done. And this process of thermodynamic evolution in a system, I think, is this process of going from being the novice when you encounter a new potential or a new situation in the environment to becoming the expert, where you're able to easily move energy through yourself with very, very little loss. So now I'm going to talk about thermodynamic computing, and this is largely a vision for where I think computing should go. So to start with, I want to make the point that the idea of coupling thermodynamics and computing is not new in any way. This is a timeline that I put together. No doubt I've left off lots of brilliant work where, it's sort of a history of computing and thermodynamics. And my point here is that both of them occurred at exactly the same time period over roughly the last 200 years. An advance in one often led to advances in the other, and oftentimes the advances in one domain were made by the same person made advances in one domain and in the other domain, okay? And this has been going on for 200 years. I believe this is still going on, okay, that we are not done, that we're going to put some really remarkable slots into this history very soon, because we're going to bring the ideas of thermodynamics and computing together again. So here I've tried to lay out sort of where thermodynamic computing might fit in the world of computing that we usually talk about today. And the way I've chosen to do this is to look at thermodynamic fluctuation scales at room temperature. Well, at room temperature is this spot right here. So on the horizontal axis, there's some characteristic time of a fluctuation, and on the vertical axis, there's some characteristic length of a fluctuation. And I put numbers here simply by looking at essentially a free electron energy. That's all I've done, okay? I've just computed it, I just set it equal to KT and said, okay, here's the frequency and here's the wavelength. So it's interesting, so at least on the spatial side, we end up at roughly 8 nanometers with this stupid back of the envelope sort of computation, which is definitely in the domain of our transistors today. And the way I've just laid out the different computing domains is, so the classical domain, which is the domain of computation that we have today, is essentially the components are all large compared to the scale of the fluctuation. And this enables you to simply average over them and to a large degree ignore them. So in this domain, the world looks mechanistic. You can talk about state machines. The scales are separated nicely, The transistor doesn't care what's going on at the smaller scale, so to speak. The gate doesn't care what's going on at the transistor scale, blah, 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 right? So that's the classical regime. Now, of course, there's a lot of interest today in the quantum domain as well. So in the quantum domain, the idea is you don't want any fluctuations at all. Or to say it differently, you want the scale of the fluctuations to be very, very large compared to the computer system that you're going to build, so that you don't have any fluctuations that matter during the time that you're doing a computation. So the quantum domain also ignores fluctuations, but in a different way. It ignores them because it gets rid of them, essentially, or that's what it aspires to do. Now, the thermodynamic domain is this domain in the middle, where the fluctuations cannot be avoided. And I contend that the primary challenges in both quantum computing and in classical computing today are that they are right at this boundary with the thermodynamic regime. In the quantum domain, the problem is I got to make the thing colder, typically, in order to get rid of the fluctuations, and that's very challenging to do, so we don't get large coherence times in our quantum systems, and they don't work the way we would like. And in the classical domain, the devices are getting so small that we can't think of them very much. We can't think of them as simple state devices as we typically do now. So the thermodynamic regime is what I call the complex multi-scale regime. It's the regime of all living systems. This is where we squarely fit. All our chemistry is right there. From another perspective, if I just look at a classical computer today and I look at the various elements within it, the transistors and the gates and so forth are definitely in the classical domain. The atoms and the small molecules of which they're constructed are definitely in the quantum domain because they're very small compared to the fluctuations. And there's essentially nothing in the middle. Okay? What would be in the middle would be things like large molecules, nanotechnologies, things like that. But we largely don't have that today. Okay, so let me take a second. So let me make a few comments about living systems and modern electronic systems. So if I look at living systems today, they take advantage mostly of chemical potentials, which ultimately comes from the sun. They work at room temperature. The interaction energies are, tenths of an EV to a few EVs. The interaction scale is molecular. And what we get out of that is these thermodynamically evolving biological systems. Now, I compare that with electronic systems today, We have electrical potentials and information potentials. They work at room temperature. The interaction energies are roughly the same. The sizes of the components that we build now are roughly the same. They're certainly getting there. But we don't have thermodynamically evolving electronic systems yet. And the reason we don't have them yet is that we're killing ourselves building systems that can't evolve, right? We're building systems precisely not to evolve so that we can tell them precisely what it is they should do. That would seem to be at odds with any goal of creating a smart kind of technology, that we should have to instruct it in every single thing it should do. But this is what we're doing. So here's a concept. Here's just some slides to give you ideas for what a thermodynamic computer might look like. No doubt it's going to look much different than this in the end, but this is where I am. So I'm imagining a thermodynamic computer as being some collection of components. You might think of them as gates or transistors or little state machines or whatever. They're connected to each other. They could be neurons, okay? And they're connected to an environment of electrical and information potential. And they take that potential and it drives the organization of this thermodynamic computer as the energy flows through it, and they expel heat into the environment at the same time. Same ideas that I mentioned, in the thermodynamic evolution of tornadoes and bubbles in water and, bacteria and so forth. Same basic idea. I'm just picking a different set of potentials to do it. So to elaborate on this simple idea a little bit, imagine you have these little cores, which are these gray and purple things, and they're evolvable in some way. And then they have some connections amongst them, so they talk to each other, and these are also evolvable. Again, you can think of these things as being neurons, and the connections amongst them, synapses, if you like. So the external potentials drive currents through the network. Energy dissipation creates fluctuations in the network. These fluctuations stabilize as the system organizes, because as it organizes, it gets rid of the heat. Basically, just lets the energy flow through it. And so the fluctuations disappear when the heat quits getting dissipated in the system. So here's a cartoon. So this actually comes from my time at DARPA, because when I was at DARPA, I tried to put together a project that I was calling thermodynamic computing. I just had no idea what it was going to be, and I never got it off the ground. But this cartoon, so imagine I've got a bunch of these cores or neurons hooked together, and I've got a problem that I want to solve. That problem is essentially the potential that's in the environment that it's connected to. The programmer, the person who wants this thing to do something, has some control over the system. So for example, the programmer might be able to go in and set the particular functions of some of these little cores. So I'm showing this in a very simple way that's saying, well, I want you to be a 1 and you to be a 0 and you to be an AND gate or something like that. So these could be fixed. Programmer would go in and say, you're this. And then what would happen is you would basically turn the system on, and it would begin fluctuating because it's dissipating a lot of energy. It doesn't know what to do with the potential that's coming into it. And as it fluctuates, it gets better at moving energy through it, and it precipitates out a structure. Okay? That's the whole idea. Now, I'm not saying this is a cartoon, right? It's not going to look like this, but that's the basic idea. It's as simple as that. So, as a few examples of things we might actually build, I call this idea the thermodynamic bit. So if you don't know this, if you take two inverters and you connect them together like I've done here, you can stabilize it in 2 states. So that's a bit. Now imagine, though, that it's a noisy bit. Okay, so typically we don't build noisy bits, we build unnoisy bits, but we're going to make this one noisy, which means we're not going to have to spend as much energy to make it do that. And so in its resting state, where there's no external potential, it can be in either of 2 states, which is this double well potential on the right side, okay? Now, I imagine that I connect it to an environment that biases it in some way, all right? And as I bias it, I make one side of the potential preferable to the other. Right? This is the potential from the external environment. There are still fluctuations going on, so this thing may be bouncing around between its various states. If I further, this as it chooses its state, it can feed back that information to its environment, which of course may affect its environment. This is what we do all the time. It's a part of its own environment. And if I add weighted connections that can change their weighting with time, then this thing can, quote, learn to become even more efficient than it is. All right, so it's starting to sound like a neural network, right? Okay, so my point here is that it's a simple, evolvable element. For some reason, we haven't built them yet. So now let's say I took a bunch of those bits and I put them together in like a frustrated network like this. This is all, I don't know if this will work or not. Then what I've got is I've got this complex set of states that are competing with each other, and I've got these evolvable weights that may stabilize it in one configuration or another. And this, for example, could be a core, one of these core elements that I had in the previous slides. Again, we haven't built anything like this. So, I have in mind a vision for how we get from where we are to the sorts of things that I'm talking about here. So I thought I'm an ex-DARPA program manager, so this is the way I think about the world. So I thought I'd just briefly say what the steps might be. We need to do some model thermodynamic system development. I'm going to show you a thermodynamic neural network model that I've developed in just a minute, where I try to capture all of these ideas. We can do what I call thermodynamic optimization of classical computing. We're not going to change the computer. We're just going to recognize that there's thermodynamics at its core, and for that reason, we could build our algorithms more effectively than we currently do. Then I think we could do what I call classical computing with classical computing systems augmented with thermodynamic elements. So we would have thermodynamic elements would be things like these thermodynamic bits, or they could be synapses, or they could be a bunch of sort of simple component features that can evolve themselves, but they're part of a system that is largely programmed. Then we could build what I call complex thermodynamic networks, so then we would be squarely in that central region in the domain space of quantum, classical, and thermodynamic. And then we could even do quantum thermodynamic networks, which I think would be extraordinarily interesting, because when you get to these small scales, you've got quantum effects for sure. There's no way you will not have interesting quantum effects. So in pursuit of some of these ideas, I and some others put together a workshop called Thermodynamic Computing, which was held in January this year, where we did a lot of brainstorming on these topics, and hopefully a report will be coming out soon, assuming people write the parts they're supposed to write, but it's in pretty good shape. So you'll be able to see sort of what we thought, and it's mostly a bunch of words, frankly, because we don't know how to do it yet, but it will talk about what the challenges are that we see and what the path might be to getting there. Okay. Now I'm going to talk about thermodynamic neural network. I guess what I would say about this is that when I started the Synapse program in 2007, I guess it was, or started working on it, and then later came to understand what the real challenges were in building neuromorphic computers, it was a very long way to get from there to this model that I'm going to show you today. And I never imagined that I would be a person to do it, but I'll show it to you. It's never been shown to anybody before, frankly, so you're the first group to ever see it. I posted the code and a manuscript online last week. It's on GitHub. If you search thermodynamic neural network, you should be able to find it. Okay. So when I was doing the physical intelligence program at DARPA, Alfred Hubler at UIUC was a physicist who did these interesting experiments with sort of putting metal balls and dielectric balls in oil and then applying potentials to them, and you could see these balls organize. It was a thermodynamic evolution sort of in a lab scale. For me, it's just sort of like stuck in my brain the first time I saw this. So I'm going to show you an example of it here. This one's from Stanford because they have a nice video of it, and Alfred unfortunately died last year. But I wanted to show you this because this is sort of what's in the back of my mind when I'm putting this model together, okay? So what's going on here is I have a Petri dish, I I don't have it. It's a Stanford. There's a Petri dish. It has some oil in the bottom of it, and there are some metallic balls in it. The outer ring of the Petri dish is an electrode at one potential, and then the wire over the top that you can see is an electrode at another potential. And this is what happens when you turn the power on. So, you know, I saw that and I said, wow, such a simple system with such cool dynamics, right? And seemed so lifelike in some way. And so that's really sort of what was stuck in my head for a long time, is how do I build even a model system that does something this simple or this complex? It's interesting, it didn't quite show it there, but once the balls make a nice conducting path between the two electrodes, the structure largely stabilizes. It essentially is predicting what its potential is very well. There's very little dissipation within it anymore, and it stops evolving. I don't know why it's not going to the next slide, but okay. So, you know, I sorted through a bunch of ideas, you know, to try to come up with this thermodynamic neural network model. And I looked for a long time at the Ising model, because of course that's what physicists do. And I couldn't make it work. There was something that it would not do. I could not make it do that sort of evolution that I saw in the balls of oil. So I came up with another model which shares some similarities to it in that there are nodes on a lattice that interact through weights that they share and that are symmetric. But instead of being a spin-based model, it's a charge-based model. So there are, what the nodes are trying to do is effectively transport charge through them. Okay? That's all the node's trying to do. Now that sounds like, you know, that should not be such a hard thing to do, but the key thing to making it work was to make sure that the charge was conserved, okay? The key thing to making this model work is to make sure the charge is conserved. And that means that while there are positive and negative charges in the model, they must both be conserved, okay? And that was sort of the key thing. That assertion leads to a bunch of equations and stuff that make this model work that I'm not going to show you. But you can look at it in the paper. I don't want to torture you with pages of equations. So you get a somewhat different Hamiltonian. You still have states. You know, the node is still choosing a state. In this case, it's going to choose a state between 1 and -1. The weights still adapt. They adapt differently in this case than they do in any, say, the Hopfield models or the Boltzmann machine models. And I'm going to take these nodes, okay, and I'm going to put them on a lattice. I don't have to put them on a lattice, but almost all the examples I'm going to show you, I put them on a lattice. I can put them in a random network. I can put them in any network that I want to. I'm going to put them on a lattice because it's easy to see what they do when they're on a lattice, because I'm going to show you a bunch of videos in a second. But this lattice, so there's a node, you know, at every intersection on this lattice. So here's a node, but there's also one along every place else. And in all the cases that I'm going to show you, the network is connected in this toroidal configuration, periodic boundary conditions, whatever you want to say. So there are no edges, so to speak, in the model. And then what I'm also going to do is I'm going to introduce some special nodes through which I can inject charge into the network. Okay? This is like the electrodes for the balls and the oil. Okay? And I can put a bunch of these, and I can make them change polarity, change potentials, do whatever I want with them. And then you're going to see the network evolve. The states of these network nodes are going to change as it tries to deal with its potential that's applied to it. And it's all in contact with a thermal bath. Okay? So instead of showing you a bunch of equations, I'm going to tell you what the basic ideas are behind the model. And if you're really interested, you should go read the paper. But here are the basic ideas. All the adaptation is by relaxation to Boltzmann statistics. That's it. Okay? There's no other adaptation mechanism in the model. There are positive and negative charges in the model, and they interact in the sense that they attract each other or repel each other, but they never cancel. Okay? I never take a positive charge and a negative charge and add it up and let it be zero. Okay? That's actually an unphysical thing to do in this model, if you think about it. External potentials can drive charge into the network. The dissipation of charge, what happens is the nodes try to conduct charge through them, but they can't do it perfectly. And when that charge that they can't conduct perfectly, they have to dissipate. They have to get rid of it. It turns out that the amount that they have to dissipate is exactly dependent on the fluctuations in the choice of the states of the network. Okay? So my point here is that the dissipation is precisely linked to the fluctuation in the network, which is what thermodynamics says it should be. Now the other thing, and this is the thing that took me forever to figure out how to do, is that the adaptation in the network is coupled also to the dissipation. All right, so the dissipation drives the adaptation of the network that makes it more efficient. Okay? So the dissipation is coupled to the fluctuation, which is coupled to the adaptation. The other thing the model does is that it can adapt itself. It can adapt its weights and the charges within the network without destroying information from prior experiences. This is a gigantic problem in neural networks, the catastrophic forgetting problem. If you think about these things as physical things rather than as being pieces of information, you can begin to see ways that you don't have to destroy stuff. You just don't do it. You just ignore it, basically. Set it aside, say, I'm just going to leave that there for a while. I'm not going to do anything with it. The long-term memory in the network is stored in the edge weights, but it also has short-term memory stored in residual charge all over the network. So the residual charge is sort of a remnant of what it's done recently that gets stuck there, and the edge weights are things that have adapted over a much longer period of time, and so they have a long-term memory. The way the adaptation works is that the first step is to do a rapid, global, reversible relaxation of all the node states. And after you've done that, you do a slower, local, irreversible adaptation of the edge states. And by doing these two things, you do a large-scale rapid adaptation and a small-scale slow adaptation, you create a multi-scale system. Okay? I think this is how you create multi-scale systems. Turns out I found some papers recently where people study this effect in nature and all kinds of systems where they adapt globally at one rate and locally at another rate. Okay, so this apparently goes on all the time in nature. I didn't know that. Okay, so the nodes can be connected as networks of any type without you don't create any dynamic instabilities. The node and edge updates are continuous and online. There are no learning rates. There's no backpropagation. Finally, the thermodynamic neural network model unifies concepts of fluctuation, dissipation, adaptation, and equilibration under a common physical model and illustrates a self-organizing complex system. Okay? And the code and everything's available. So let me show you a little bit about how it works, okay, and what it does. So what I'm showing here, if you remember the torus that I had earlier, I've just spread out the torus. And each of these squares represents a node state, okay? And each node is connected, in this case, just to its four nearest neighbors. There's a weight that connects just its four nearest neighbors. If it's white, it means the state is 1. If it's black, it means the state is -1. I'm not visualizing any of the weights, just the node states. In this case, there are no external potentials. It's just the nodes talking amongst themselves in contact with a thermal bath. So the interesting thing that happens here is this charge conservation idea forces the network to the network wants to organize sort of asymmetrically or antiferromagnetically. So it wants to create domains, black and white checkpoints, okay? So it can't do so perfectly in this case because the thermal fluctuations are driving it all over the place. The thermal fluctuations won't let this, in this particular case, won't let it settle down into a perfect checkerboard. So if I played you a video of this, you would see these checkerboards sort of moving around everywhere, and I'll show you some in a minute, okay? Now, it's really hard to look at these checkerboards all the time. So what I do is I simply just, in the display, all I do is I just invert the polarity of every other node in the display. I'm not changing anything about the model, I'm just making the display different. And if you do that, then you see the domains look like either black, mostly black, or mostly white, okay? It's exactly the same thing, I'm just changing the display. So in this case, you can see, okay, this was mostly black, some white things, white domain surrounded by black, okay. Now this is what happens when I introduce a potential. Okay, this is one node in this case, just injecting a positive charge into the network. And what happens is it polarizes. What happens is the node polarizes, the bias node polarizes the nodes around it, as you might likely expect. It's injecting charge into the network, and this is forcing its nearby neighbors to change their state or to stabilize their state. And the scale of the polarization depends on, the scale of the potential that I apply. So I apply a larger potential, I get a larger region of polarization. It turns out that because of this antiferromagnetic order, there are essentially two partitions in this network. And whether I put the positive node in, say, partition 1 versus partition 2, makes it polarize the partition either black or white, okay? That's something of a subtlety. It's actually a very important thing, this sort of partitioning of the network. All right, so this is what happens if I put potentials of opposite polarity in the same small network. What happens is, as you might expect, they're trying to connect to each other. This guy is injecting positive charge, this guy is injecting negative charge, and essentially the network is evolving to be able to transport charge from here to here and from here to here, okay? So here's a black domain, here's a white domain doing it. This is what happens when I try to do it and they're essentially in the wrong partitions. Then what happens is they just set up a domain wall between them, okay? That's going to sound a little weird to you at first, but it's so important to be able to build these domain walls where you need them. If you can't build a domain wall, you just wipe out everything that you learned before. Okay? You've got to be able to wall off what you don't want to do right now. So here's what happens if I just have two nodes of the same polarity. If they're in the same partition, they basically jointly polarize the region around them. They actually don't grow weights that are large between them. They just polarize. Here's white on the top. Here they're in opposite partitions, so again, you get a domain wall. They polarize differently. Okay, so now I'm going to show you some videos of these networks evolving. Okay, and in the first case, it's a larger network. Again, it's a nearest neighbor network. Every one of these little dots is a node just connected to its nearest neighbors. No external potentials in this case, just the thermal bath. And so here's what happens if you just turn it on, okay? So you can see it's ordering, but there are fluctuations that are the same scale of the things that are holding it together. So it's doing this constant sort of dance. And when I first showed this to somebody, they said, that looks like Glauber dynamics in Ising models, okay? It does look something like that. All right, so that's one example. So now I'm going to show you another example. In this example, I've set up the system so that it wants to order, basically. In this particular case, I've given it more connections. Each node is connected not just to its 4 nearest neighbors, but to the 16 nearest neighbors that are in the same partition, that are in the opposite partition that it is in. And oh, by the way, in every case, I'm starting off these simulations with just a bunch of random numbers for the weights and a bunch of random states for the nodes, okay? So in this case, it wants to order more strongly because it's better connected in this case. It's interesting because it sets up these stripe domains, and you can see the fluctuations along the domain walls. You can also see the fluctuations within the domains, which are these sort of white and black dots. Oh, by the way, this is just in this case, for most of the examples I'm going to show you, I can let the nodes, they can be binary, they can assume multiple states across -1 to 1. This is just a binary node state. So here's one where the nodes are connected. Let's see, which one is this one? Okay, similar to the last one, each node is connected to its 16 nearest neighbors that are in the opposite partition. Each node also has recurrent connections, so it's feeding its own state back to itself all of the time. And I've chosen the temperatures to be just near a phase transition, okay? Just near the transition where it would want to go to almost entirely one domain to not ordering. And so this is what happens. So you get stronger temporal dynamics because of the recurrent connections in the nodes. You'll see domain structure grow slowly because it's just below the boundary for the transition. It's actually more interesting to see it in a somewhat slower motion because it changes so quickly, it sort of looks too, it's hard to follow in this one. But so you can see large domains forming. You can see interesting fluctuations. The fluctuations here, sort of these on, that are thermal fluctuations on top of the domain, these are really cool looking. I don't know what the heck's going on here, but it's not simple noise. There's definitely some structure there. So now what I'm going to do is this is again a nearest neighbor network, just connected to the 4 nearest neighbors. There are 16 pairs of bias nodes in this network that are changing potential periodically, but with different periods, okay? So what you're going to see is the network organizing to move charge amongst the various bias nodes, okay? And in this case, you're also going to see, I mentioned that the adaptation includes a global equilibration step, which is essentially a Markov chain Monte Carlo technique that samples a whole bunch of node states. You're going to see that here, and what that looks like is the propagation of potential through the network, okay? So that'll become clear in a second. But, okay, so you can see these tiny little things that are green. These are the bias nodes. They're just distributed all over the place. Some are positive and some are negative. They're paired, and they're changing potential with different periods. When they change potential, when the bias nodes begin to change potential, that's when you see these bursts from black to white or white to black around the bias nodes, okay? And what happens is, as the network evolves, its dissipation becomes lower, it becomes better and better at connecting the nodes together in such a way that the charge is transported efficiently. And you kind of see this, you'll also see a kind of modularization of nodes in the vicinity of a bias node, in the sense that, they become sort of a domain that's either black or white and switches depending on the configuration of the bias nodes. Okay. One more time, I just want to make the point that they don't have to be these nearest neighbor networks. In fact, networks that are connected differently avoid a lot of geometric problems when making connections in sort of nearest neighbor networks. So this is a network in which there's still 4 connections per node, but it's a random network. And there are a bunch of bias nodes in here, 16 pairs, just like in the last one. And, you can see stuff is going on. It's just you can't really derive a lot of intuition from it. But you can do random networks, you can do hierarchical networks, you can do pretty much any kind of network you would choose to build. Okay, so a few comments about the model. Here I'm plotting a chart of energy versus entropy, and I'm sort of thinking about what's going on in one of these nodes as it's evolving. And what's going on is when potential changes, work is done on the node, okay? When work is done on the node, it turns out its energy increases, all right? But its entropy also increases because it's not in a nice little state where it's conducting charge very well, all right? Its entropy actually increases. And so this is sort of what I call the fluctuation and equilibration part of the path. And then what happens is the node has errors, essentially. It can't transport all the charge through it. It dissipates this charge as heat, essentially, into the thermal bath. And this is the dissipation and adaptation step of the network. Okay? So that's sort of the basic thermodynamic idea of what's going on within the nodes and also within the network. I think I'll make a few. How much time have I got here? I'm done. All right, I'll skip these. Let me just go here. Okay, summary. So summary is, I think the current computing paradigm and technology are mature, but the performance is still far from fundamental limits. The challenges to the current computing paradigm are all thermodynamic. They are power consumption, fluctuations, and self-organization. The long and interdependent histories of thermodynamics and computing are not over, okay? We are poised, I think, for an enormous conceptual and technological breakthrough in this field. Modern electronics are well suited to the development of a new class of computing systems that I call thermodynamic computers, and we now begin to see a path for how we might get there. And the thermodynamic neural network is a model system that unifies these concepts of fluctuation, dissipation, adaptation, and equilibration into a self-organizing complex system. So why is this so hard? You know, I've been saying these things for the better part of 10 years, not in the large, well-spoken way maybe that I was able to do today, or hopefully I did it today. But I've been saying these things for a long, long time, and I find that people have a very, very hard time with these ideas. So I thought I'd make a few comments about why I think they're hard. So the ideas presented here essentially contradict the prevailing mechanistic cause and effect brain as a machine computing paradigm. They contradict the current computing practice where the systems are designed to prevent evolution. They cannot be described within the current computing paradigm. They imply that the universe, largely to me, they imply that the universe is uncaused and evolved from a thermodynamic singularity that doesn't have a precedent. That's not exactly a new statement. But they also imply that causation is the product of evolution and not the other way around. Now, in everyday life, this is transparent that causation is the product of evolution, but for some reason, in communities of people working on technology, they fail, I think, to recognize that fact. So we have the cart before the horse because we don't know what the horse is. The horse is thermodynamic evolution. It's the thing that makes stuff. We're looking at all the stuff. That's the cart. And there's a ton of it. And if you look around, we're so overwhelmed with all the stuff, but we don't know how any of it got here. It's the getting it here part that matters. And so we are trapped, I think, in certain unresolved paradoxes that have been around for a long time. And they're the first cause paradox in philosophy, they're the reductionist paradox in physics, and they're the where do algorithms come from paradox in computing. I mean, it has frustrated me forever to walk into a room of computer scientists and ask the question, where do algorithms come from? And be looked at like I'm out of my mind, right? Well, how can you have a field of computing which depends intimately on algorithms and not ask that question? So, I believe we're stuck in a social, cultural, technological, and scientific local minimum, okay? But I think we are in position to get out. That's it. Okay, thank you all.